Now that we've discussed the particle nature of photons, we need to come back and see how that jibes with the original wave nature that we've already explored. We know that if we send in light waves through two slits, the waves diffract at each slit, interfere, and form an interference pattern like this. Now, what would happen if this incident wave was weak enough that we could detect individual photons? Essentially, with a strong wave, there's many, many photons coming, and we would detect a whole bunch of them over here. Well, if it's a weaker wave and we place a detector here that can detect individual photons, what we find is that wherever we place the detector, we get a random time series of photon detections. However, in regions where we would have a bright fringe, we get a much more rapid time series. In other words, the photons hit much more often. In regions where I've got a dark fringe, the photons are much less likely to hit. So in other words, these interference fringes become areas of high probability and low probability of getting a photon hit. And that probability is simply proportional to the intensity. But we also know the intensity is proportional to the electric field squared, and the electric field is what was waving. This was an electric field wave. So the probability of a photon being detected is proportional to the wave amplitude, the electric field, squared. That's what's being stated in this box right here. The probability per unit time interval that a photon will be detected in any small volume centered on a given point in a light wave is proportional to the square of the amplitude of the wave's electric field vector at that point. We next ask the question, what if this incident light is very, very weak? So weak that we would never have more than one photon in here at a moment. Then you would ask the question, can that single photon really interfere with itself? Could I really get areas of high probability and low probability, or will it just be even probability all the way across? After all, we would expect one photon to either go through the top slit or the bottom slit. However, when we perform the experiment and use a very faint light beam so that there's never more than one photon, over time we still build up this same fringe pattern. We still find areas of high probability and areas of low probability. In other words, even though we send one photon, it still seems to be passing through both slits, interfering with itself, and giving us an interference pattern. Some people have thought to try and catch the photon going through both slits at once by placing detectors at the slits that don't stop the photon but do measure that it went through. Surprisingly enough, when you do that, the photon doesn't go through both slits. It goes through just one or the other. However, when we do that and force the photon to go through one slit or the other, then the diffraction pattern does disappear. We lose any interference because we've forced it to choose one side or the other. People have also suggested that maybe we can explain this process of going through both slits at once if we imagine that the photons are just very small wave packets. So they're small enough that they appear to make a single point on the target, but big enough to get through both slits. However, we can set up a two-slit diffraction pattern where the two slits are very widely spaced. So here's an experiment described in the book. We send a single excited molecule through. It radiates light, and we don't know which path it's radiated that light along, but it could have sent it this direction or this direction. Either direction, it hits a mirror. The two mirrors are far apart, and then they bounce back here to this point. This is a half-silvered mirror, so there's a possibility of this light going through it and a possibility of this light bouncing off of it. so that both paths take me back to the detector. So I still have two different paths, but they are widely spaced. There's no way a narrow beam, a narrow photon that still has some width, could hit both of them. And yet, if I move this half-silvered mirror back and forth, I still get a diffraction pattern. I still get interference fringes, regions of a high probability of detecting a photon at the detector, and regions of low probability. In other words, when the photon leaves the source, until it reaches a detector, it essentially explores all of space. It acts like a great big wavefront going everywhere. But as soon as I try to actually make a measurement of it, then it collapses to one single point, becomes a photon at one point in space and time. It acts like a wave while propagating, and acts like a particle while interacting.